Hi everyone. In this session, we are going to see about the structures of IIR filters, that is infinite impulse response filters. So the outline of this presentation is going to be in this way. That is, first we are going to realize the structures which are available in IIR, direct form 1 and 2, cascade form realization and parallel form realization, and after that we look after the implementation of it in problems. So what are the outcomes? At the end of the session, you will be able to realize and implement infinite impulse response filters by using different structures, and it will create an ability to determine the system transfer function using block diagram representation with the corresponding difference equation. Right? So with that outcomes, we'll start with the realization of structures in IIR. What is a discrete time system? A discrete time system is one which accepts a discrete time signal as input and it processes it and delivers the processed discrete time signal as output. So this is mathematically expressed or represented by using a difference equation, isn't it? So it can be realized or implemented as a digital hardware, like by using microprocessor or microcontroller, or as a software running on a digital hardware like our personal computer. So processing by the digital hardware involves mathematical operations like addition, multiplication and delay. So these are the three major operations that are involved. Okay, the time taken to process the discrete time signal and the computational complexity depends on the number of calculations involved and the type of arithmetic used for computation. Okay, so these issues are addressed in structures for realization of discrete time systems. From the implementation point of view, the discrete time systems are basically classified as IIR and FIR systems. So the various structures proposed for IIR systems attempt to reduce the computational complexity. That is, if you reduce the number of elements that are used for addition, multiplication and delay, they say the computational complexity is reduced and the errors in the computation is reduced as well. Okay, and in turn it reduces the requirement of memory and finite word length effects in computations. So with we'll continue to the actual mathematical representation of a difference equation. We have already seen what is h of z and we are familiar with this z domain. Okay, so h of z is actually the transfer function of discrete time IIR systems. The general representation of an IIR system is h of z can be represented as B0 plus B1 z inverse plus B2 z to the power of minus 2 plus etc. up to Bm z to the power of minus m divided by 1 plus A1 z inverse plus A2 z to the power of minus 2 plus etc. up to An z to the power of minus n, where A series and B series are An and Bm are coefficients. Okay, so what is x of z and y of z? See, when you are considering a system and the transfer function of the system is h of z, obviously we would have given an input and that would yield an output, right? So the input of the discrete time system in the z domain is considered as x of z and the output of the discrete time system in z domain is considered as y of z. So h of z is equal to output divided by input, that is y of z by x of z, which is already told. So the same equation is repeated here. Okay. Now, what is the next step? Just cross multiply on both sides. So cross multiplying the equation, what will we get? Y of z into this one. So into 1 plus A1 z inverse plus A2, this equation, and x of z has to be cross multiplied with this numerator. Okay. So equating that on both sides, what do we get? So this z is is actually delay elements that we know in Z transform. So, on taking inverse Z transform of the above equation, we know that Z of x of n is x of z, whereas Z of x of n minus k is equal to Z to the power of minus k into x of z. This is actually shifting property, right? So, while using this, if the element is Z to the power of minus 1, our inverse Z transform will become y of n minus 1 or x of n minus 1. If the Z value is Z to the power of minus 2, we will get x of n minus 2. So, while taking inverse Z transform on both sides, we get an equation finally like this. Y of n is equal to minus the summation of m is equal to 1 to n am into y of n minus m plus the summation of m is equal to 0 to m bm x of n minus m. So, this is a general difference equation of an IIR filter. Right. So, in general, the time domain representation of an nth order IIR system is. So, normally the order of the filter is very, very important while designing a system. Right. That too in IIR. So, y of n is considered as the same equation, we have written it here, and in the Z domain representation, the nth order of the system is represented as the equation which we have quoted previously. So, the above two representations of IIR can be viewed as a procedure or algorithm to determine the output sequence y of n from the input sequence x of n. So, also in the above representations, the value of m gives the number of zeros. So, this m decides the number of zeros and the value of n gives the number of poles in an IIR system. Okay. So, what are the different forms or structures for realizing this IIR systems? They are direct form 1 structure, direct form 2 structure, cascade form structure and parallel form structure. So, we will go through one by all the structures one by one. First one is direct form 1 structure. So, we are considering the same general governing equation of an IIR system. So, this is the equation. Now, while taking inverse on taking Z transform, what do we get? This is the equation. So, how are we going to apply this? Output is equal to input portion. Okay. So, from structure for direct form 1. From the direct form 1 structure, it is observed that the realization of the nth order discrete time system with m number of zeros and n number of poles involves m plus n plus 1 number of multiplications and m plus n number of additions. So, these are the computations that are said to happen. Also, this structure involves m plus n delays, and so m plus n memory locations are required to store the delayed signals. Okay. So, when the number of delays in a structure is equal to the order of the system, let's say if the number of delays are equal to the order of the system, then we call that structure as canonic structure. But in direct form 1 structure, the number of delays is not equal to the order of the system, and so direct form 1 structure is called as non-canonic structure. Okay. So, what are the elements that we require while drawing a structure that in whatever form we require? So, the basic elements of a block diagram are adder, so a constant multiplier, a unit delay element and a unit advance element. So, here we have both time domain representation and Z domain representation. So, how can we represent an adder using a time domain representation? Adder is used to add two signals. Let's say the two discrete signals are x1 of n and x2 of n. So, use a plus symbol and with an arrow, the output of this will be x1 of n plus x2 of n. The same thing, after taking z transform, what will we get? Z of x of n is x of z, right? So x1 of z and x2 of z gives the output x1 of z plus x2 of z. So it is as simple as drawn. What is a constant multiplier? So x of n is the input signal. It has to be scaled up by a multiplier a. So if you are putting the coefficient inside a triangle, it becomes a multiplier. So the arrow mark represents the input given as x of n. After multiplying it with the coefficient a, it becomes a into x of n. The same thing while taking z transform. How is it getting transformed? X of z is going to be the input going through a multiplier a. The output of it will be a into x of z. Okay. So what is unit delay element? Unit delay is one unit delay, 1. Okay, so x of n, when it is entering inside z inverse, it is unit delay element. So depending upon the number of delays, we can append the z inverse boxes. Okay, so this gives an output x of n minus 1. So z inverse to the power of minus 1 represents x of n minus 1. The same thing can be expressed in z domain as the input is x of z. It goes through a delay element z inverse. So what will be the output of it? It is z inverse into x of z. Okay. So unit advance element. Here advance in the sense to the power of positive value. Okay. So x of n goes inside advanced element z. Z means z to the power of 1. So in that case, how the shifting will be x of n plus 1. So similarly, in the z domain, it is getting reflected as x of z getting inside z comes out as z into x of z. So these are the basic things that we require in order to form a structure in IIR systems. Okay. So this is actually the structure of an IIR system using direct form 1 structure. You can look at this. I am giving an input x of z. The output is y of z. See, we have multipliers such as b naught and a naught, a1, a2. Whatever is the multiplier we have, we know the difference equation of the system. So this is actually a general block diagram. See, these are adder elements. So what does it look like? Y of n. See, this is actually the feedback. So feedback y of n. When I am giving it to a delay element z inverse, this portion, this particular node point becomes z inverse into y of z. This is what we saw. So while it is given to a multiplier minus a1, so this structure is actually drawn for the general difference equation, governing equation of an IIR system. So minus a1, which is in turn given to an adder. So see how many number of elements, delay elements, multiplier elements, adder elements are added, which makes the structure more and more complicated, which is not actually serving our purpose. Okay, so this is actually the general form of representation of direct form 1 structure of an IIR system. Probably this you can make it clear while doing the problems. Okay. Then direct form structure 2. See, in the direct form structure 1, we are wasting so many number of elements, is it not? So to reduce the number of elements, we are going in for this direct form structure 2. Here we are getting into a common function called as weighing function. Let us look into the general difference equation governing an IIR system. So this is actually the general equation. When I am expanding this equation, I get these terms. It is expanded according to a summation of m equal to 1 to n and m equal to 0 to m. Okay, so while taking z transform for the above equation, we get a sequence like this. You know to take a z transform, right? So now Finally, obtaining y of z divided by x of z, you get an equation like this, which we already know, which is a transfer function h of z, right? In the case of direct form 1, we directly cross multiplied it and we have drawn the diagram for direct form 1. Whereas here, what we are going to do, y of z divided by x of z is equal to, we are inserting one common function called as weighing function, w of z. The same thing I am multiplying and dividing by the weighing function, which is equivalent to the same value y of z by x of z. So just look into it. I am just separating the transfer function, or splitting the transfer function as w of z by x of z into y of z divided by w of z, where w of z is multiplied and divided. Okay, so the first half, since it's in the multiplication format, the first half can be considered as w of z by x of z. So w of z by x of z is equal to 1 divided by 1 plus a1 z inverse plus a2 z to the power of minus 2 plus etc. up to an z to the power of minus n. So the other part is y of z divided by w of z. That can be written as the remaining numerator part. So now take the first equation. While cross multiplying, you will get w of z and x of z in the previous equation, right? So now you consider the output of the first stage as w of z, and equating this equation to w of z, you bring all the rest of the coefficients to the right hand side, whereas you keep w of z in the left hand side. Okay, so the same thing happens for this equation also. Just cross multiply, because the output is y of z, you cross multiply and bring all the coefficients to w of z. Okay, so what is happening in the direct form structure 2? The realization of an nth order discrete time system with m number of zeros and n number of poles involves m plus n plus 1 number of multiplications and m plus n number of additions. In a realizable system, n cube m, and so the number of delays in direct form 2 structure will be equal to capital N. Hence, when a system is realized using direct form 2 structure, n memory locations are required to store the delayed signal. Okay, so this is actually the general block diagram for the governing equation of direct form 2 structure. So here you can look at, you can just hold your right hand side, you can hide this part and look at the system. We are giving an input signal x of z, and the output for this particular set is w of z. Okay, so this is the first half of the equation. So first half of the equation I can derive it using that equation. We re-equated, right? W of z is equal to, so with the help of delay elements and multipliers and adders, we can now bring in the same equation. We can obtain the same equation. So now this has become a common point. So what happens here? The number of adders as well as the number of delay elements are added or proportionately reduced, which makes this delay elements a common pipeline. So we are now creating multipliers for the other end, that is y of z divided by w of z. So the next half of the equation, we are considering w. You forget about this, or you hide this portion and look at the system input will become w of z and the output will become y of z. So here we have already written the equation. Next half, y of z is in terms of w of z. So using that, we can use this structure. We can use this structure to obtain direct form 2. So this is the generalized structure, and here we can simply look at, this is capital N is equal to M. So this is a perfect canonic structure, whereas direct form 1 cannot be a canonic structure, because the delay elements and the order of the system will not be equal in direct form 2. Okay. Yeah. So conversion of direct form 1 to 2. This is how. This is your direct form 1 to 2 conversion. Yeah. So how do we convert it? H of z. In direct form 1, we take x of z passing through the system which has transfer function h, which gives y of z. Whereas x of z can be given to h1 and h2, that is two transfer functions, and it can be taken as y of z. Or otherwise this can also be done h2, h1 and then y of z, or simply having h. We call that function as w of z, right? So this is a convert. The next structure is cascade form structure of an IIR filter. We all know what is a cascade form structure, right? The transfer function can be expressed as a product of number of second order or first order sections as shown in the figure. So cascade is a series of transfer functions multiplied together, that is h1 of z into h2 of z into h3 of z up to hm of z, which is nothing but the product of I is equal to 1 to m hi of z, where hi of z can be the coefficients of a second order section or a first order section. The individual second order or first order sections can be realized either in, we can, one more thing, in cascade form, we can design it using direct form 1 structure or otherwise direct form 2 structures. The overall system is obtained by cascading the individual sections as shown in the figure. So the number of calculations and memory requirements depends on the realization of individual sections. So cascade in the sense h1 of z, h2 of z, h3 of z up to hm of z, which gives our y of z, right? There are some difficulties in cascade structure while designing. So decision of pairing poles and zeros becomes so difficult. Deciding the order of cascading the first and second order sections become a difficulty. Then scaling multipliers should be provided between individual sections to prevent the system variables from becoming too large or too small. So we are supposed to provide individual sections to prevent the system variables. Okay. So last section is parallel form of an IIR structure. Parallel, hopefully you can understand, it is addition. Parallel in the sense one after the other. Series will be cascade, parallel will be addition. So a partial fraction expansion of the transfer function in Z inverse leads to the parallel form 1 structure. So assuming the simple folds, the transfer function h of z can be expressed as h of z is equal to c plus the summation of k equal to 1 to capital N ak divided by 1 minus pk into z inverse, where p is the poles. Okay. Right. So there are two forms of representation. The direct partial fraction expansion of the transfer function z leads to a parallel form 2 structure. So here the transfer function can be assumed as wk of n is equal to minus ak1 into wk of n minus 1 minus ak2 wk of n minus 2 plus x of 2 x of n. So from this the final equation is y of n is equal to c into x of n plus summation of k equal to 1 to k y of k into n. That is purely by using partial fraction method. So this is actually the block diagram representation. So you can see parallelly added. Okay, so the h1 of z, as how we did for cascade, there is one form of representation. So constant plus h1 of z, h2 of z up to hk of z, or otherwise as such as our normal parallel normal forms we can design with the coefficients. This is minus ak1 minus ak2, this is bk0 bk1. Like this we can design by using the partial fraction method. There are two forms available. A partial fraction expansion of h of z is equal to a problem is given here. So it can be, see how can we do this? By using long division method. Hope you all know what is long division method. So while using a long division method, you get this constant plus these functions you will get. And by so the corresponding parallel form 1 realization can be obtained using this structure. Okay. Probably we look at a very simple problem, and if you have any doubts you can ask form. Okay. So likewise, we can do it with the partial fraction by using form 2. So this is obtained by using partial fraction expansion of h of z. Okay. Yeah. So this is the generic formula which I have already explained. Once again, this is one more problem which can be obtained or which is obtained by using a long division method. So forms can be equally expressed. So with the second order section, we can draw this parallel form like this. Okay. Right. So this is with first two first order form with first order section. So with the second order section as well as first. Go back to the slide and see. So this is the equation I have used. Okay. So using that delay elements and 0.7, you can multiply it and you can find out the structure. You can draw the structure. Okay. So obtaining the equation is the important task for us. Yes. Well, how can we draw a direct form 2? So direct form 2, as I told you earlier, w of z divided by x of z, the same transfer function, split it into 2. Obtain two different equations. The structure like this. Separating the common is using the common delay elements and separating the multipliers and adders. So this is the way we are using to draw direct form 2 structure. Cascade form realization of a digital system. So an equation is given. The first and foremost step is to take Z transform on both sides, take Z transform, obtain the transfer function. We are getting this, and now we can split it into two components so as we get h1 of z and h2 of z. So h1 of z is this and h2 of z is this. Now we have a choice. We can draw two different realization structures for this cascade form. Either I can use direct form 1 or I can use direct form. So this is by using direct form 2, we have drawn the structure for the cascade. So this particular portion represents h1 of z and this portion represents h2 of z. Okay. Right. The same problem I have taken to solve for all the forms. So equation is given. In that we are going to find out the direct form 1 structure. We are going to draw direct form 2, cascade form and parallel form realization of the system, right? So first and foremost step is taking Z transform on both sides, obtain the transfer function, and this will be more than enough for your for drawing the direct form 1 structure. Okay. So draw the direct form 1 structure. Hope you understand how to draw the structure, right? So direct form 2, the same procedure. Hope you remember w of z by x of z into y of z divided by w of z. Okay. So using that procedure, we can obtain direct form 2 structure like this. Then finally cascade form. Cascade form is splitting into 2. Since it is a multiplication component and it is in series, you need not worry, ma'am, whether I am taking a correct numerator or denominator. Doesn't matter. Anybody can take any numerator and any denominator and form the cascade form of the system. Okay. So h1 of z is this and h2 of z is this. So normally for cascade form we prefer to draw direct form 2 structure as it is reducing the number of computations as well as the elements that we are going to use in the system. Okay. So finally parallel form, the same transfer function. By using long division method we get this. So minus 3 plus still it is an equation with the power of power raised to 2. So power raised to 2 in the sense we know the partial fraction. It is first factorize into 2 factors. There are 2 different poles obtained. So first factor is a divided by the first pole, b divided by the second pole. Use the residual method. we know the residual method for applying, right? So use the residual method at Z inverse. Substitute at the value of Z inverse is equal to. So obtaining that, we can find out by using find out A and B using partial fraction method. So after obtaining the partial fraction, we are naming that functions as h1 of z and h2 of z. So this is how we draw the parallel form structure. Okay. So C is a constant. So this is actually parallel form 1 structure. C is a constant. Hope you can relate this with the general structure we have drawn. So C plus h1 of z is this and h2 of z is this. The same thing you are going to do, but we are going to draw parallelly, that is using different adders. We are going to obtain the function. Okay. So for the same problem we have done 4 forms. Finally, the comparison of different structures. The major factors that affect our choice of a specific realization are computational complexity, memory requirement, and finite word length effects, assuming that m is even with m equal to n, whereas this m is not equal to n in direct form 1 structure. Okay, so in direct form 1, canonic form is direct form 2, and cascade form and parallel form, the multiplications are 2m plus 1, addition performed are 2m, and only in parallel form it is 3m by 2 plus 1, whereas the registers that it is consuming is 2m in direct form. See how drastically it has reduced from direct form to. So we employ only m registers for storing the elements in all these forms. So that so the assignment for this particular session is the assignment in forms is very specifically this one. All these 4 problems are university problems, very important problems for examination, but those are very easy. If at all, if you have any doubts, you can ask me. Okay, so thank you so much for listening very patiently. Thank you so much.